Warahmatullahi wabarakatuh, and good morning. I greet to Dr. Azim and my group member. So today we'll present about the topic dam-free vibration, and we are from group J. We'll present about question number 8, and this is my team member, which is Nur Najiha, and the second one is me, Muhammad Ikmal bin Masaad, on Junlin, Farhan, and also Aiman Fitri. So I will start the present about the question number 8.39. For the question number 8.39, it is about a cannon which fire a cannonball, and at the chart of the cannon, it has a damper and also a spring stiffness. As for the given information, the mass of cannon and chart is 750 kg. Mass cannonball is 4.5 kg. The stiffness of the spring is 27 k. The damping, the damper coefficient is 9,000 k, and the velocity of the cannonball is 350 meter per second. For the free body diagram of this problem, as necessary that it is have a damper at the, it has a damper and the spring at the left of the chart. So it will, the direction of the damper and the spring will go to the left, and it also have a force that will vibrate it the red to the right, and it also have a weight which is equal to mg and also the normal. And for the kinematic diagram, as you can see from the theory diagram, that spring and damper in the left, so the acceleration will oppose the spring and damper, and the acceleration will move to the right. Thank you. So I will pass to Aiman Fitri.
So thank you very much, Ikmal, for passing to me. So after the free body diagram, we must proceed to the next step in order to complete the question. So for the step 1, we want to determine the natural frequency. As we know, the natural frequency will be used to find zeta, and also the information to find the natural frequency has been given in the question. So we just put it in the what we call equation, k over m. I mean square root k over m. So we get the natural frequency, and for the next step, we find zeta, which is equal to c over natural frequency that we find in the first place. So we get 9,000 over 2 times 6 times 750, and we get 1. When we get 1 for the zeta, it is automatically critically damped. Thank you. That's all for me. I will pass to the next presenter.
Okay, and I'll be explaining on the step on how to determine the velocity of the cannon and also kite. Okay, so first step we have to do a linear momentum equation in horizontal to find the cannon and kite velocity. So from that we assume that in the right direction is a negative. So you can see that there will be 750 is that the mass of the cannon, and the x dot is we want to find the velocity of the cannon and kite. So from that equation, we equal to 0, and then we obtain the velocity. So as Aiman mentioned, the problem is related to critically damped. So we have to use the equation x equal to a plus a2t e power of natural frequency and t. So that's the equation for the critically damped. So we have to differentiate the equation to obtain the velocity, which is x dot, using product rule, and from that we can obtain the final, which is x dot equal to this one. And then next June we continue proceed the solution.
So Thank you, Gia. So for next step, we'll be continuing on initial condition where we assume that when t equals 0, x is equals to 0, and x dot, which is velocity, is equals to initial velocity, indicate by x dot naught. And by using the equation that we obtained just now, which is x equals to a1 plus a2t, e negative omega nt, this is actually the critical dam equation. And by using the second equation, which Dia showed just now after differentiating for s naught dot, we will obtain both a1 and a2 by using the initial condition, which is x equals 0, a1 will be equals 0, and when we substitute t equals 0 and x dot equals x naught dot, we will obtain that a2 is equals to x naught dot. And note that in the previous session, we obtained that a2, the x naught dot is equals to 1.41, which then a2 will be equals to 1.41 as well. And after that, using the same equation for x naught dot, we substitute a1 and a2, and we'll get an equation. And we substitute a1, a2, as well as natural frequency, we'll get a final equation, which is x dot equals to negative 8.46 e negative 60 plus 1.410 e negative 60. So to determine the maximum displacement, the energy knowledge or energy theorem is used, where at a higher potential energy, the displacement is at maximum, whereas the kinetic energy is at 0. So when the kinetic energy is equals to 0, the velocity is equals to 0 as well. So thus, by substituting x dot equals to 0, we obtain that t equals to 1/6s. So that's all from me.
So thank you, Jude. For the last step, after we already got the answer for t is equal to 1/6, we substitute the answer t into the main equation for critically damped, which is x is equal to a1 plus a2 t exponent negative omega n t. So, so we already know that a1 is equal to 0 from the initial condition. We substitute all the value into the equation and put the 1/6 for the t, and then we get for the x max we get 0.0864 meter. So that's all for our group. Thank you.